We're back again. All right, so we should have made it through the review PowerPoint before taking our time to watch this one, because we're going to start talking about some new concepts. Some of this stuff's not going to feel so new, but there's definitely stuff later in the PowerPoint that is new, especially compared to what we've been dealing with in the previous electrical class. Um, these Some of these concepts are going to apply directly to the lab that we're working with this week. Some of them will apply more to some of the work that we'll be doing in the future. So off we go. Wire types. So in a car, we're going to always use stranded wires. The stranded wire is flexible, so that makes it so as we're opening and closing doors, as the engine is torquing and moving the wiring harnesses that are connected to it, the wires will last a lot longer. The strand, we may even have one or two of the strands inside the wire break as time goes by, but because there are multiple strands, current can still flow through it. But the majority of the reason why we use stranded is just because it's much more flexible. It's more expensive than if we had a solid core conductor, just because there's more work that goes into making that piece of wire versus the other. But it's what we have to have, and broken wires happen in like our harness that goes into the doors of vehicles very, very often. So even stranded wires not quite up to some of the challenges, but it lasts for a long enough period of time that the manufacturers feel like they're putting in the best possible option. The solid core wire is really mainly used for industrial components, and also all the wiring inside the walls of our houses and buildings and things like that are solid core, because really there shouldn't be any movement that's going on there. My wall is not going to move from here to there, and if it did, then I might be looking at some other type of conductor. The wires that we tend to see, and this depends on what manufacturer you're working with, but here in the United States we use the AWG style, and that is, it must have been some government official that was tasked with creating this system, because as the wire gauge gets bigger and bigger, the number gets smaller, right? That doesn't make sense. You think that the thicker the wire, the bigger the number. No, it's the opposite way around. A 18 gauge wire tends to be one of the smaller wires that we'd come in contact with on a vehicle. Some of our like little switches and stuff will use 20 or even smaller gauge, but that's because there's not really much of any current that's flowing through. But the takeaway from that is the bigger the number, the smaller the wire for the American style of wire gauging. And then for metric, which is what we would see from imports, Volkswagen, most of our Asian vehicles, metric, right? Because these countries use the metric system because they're not as stubborn as we are. These are the diameter squared of the wire. So this works the way that you would think it should work, is the bigger the number for the metric system, the thicker the wire is. So down here at the bottom, that 19 metric sizing for a wire and a 4 gauge, we're getting up towards like battery cable sizes there. The wire, based off of how thick it is one aspect that will help to limit resistance, right? A thicker wire is going to have less resistance than a very, very small, thin one. But also the length of wire plays a big part in how much resistance there is in a circuit. A coil of a relay is just a really, really thin wire that's like 100, 150 feet long, and those can have resistances up to 80, even 100 ohms in some cases. So there's no resistor there built into it that's creating resistance. It is just the coil of wire that is adding up to the resistance of that circuit, dropping the voltage as the current flows through it. and creating that magnetic field that makes the switch close. Just a practical look at actual grounds and body grounds here. The hood of the vehicle has a ground strap attached to it because there must be some sort of a light that's attached up there is often a reason for it. Here they're talking about it helps to reduce radio interference because we build up static electricity on the hood as we drive down the road. Think about wintertime getting out of the car and being afraid to close the door because it's going to zap the crap out of you, right? So, different ground pathways. On some vehicles, we have to start being careful about what kind of wiring we get into. So on a hybrid electric vehicle, we have voltages that can go all the way up into the hundreds of volts, and that's even AC when you get inside of the transaxle. So, that will definitely kill you. So when we see wiring harnesses with funny colors on them, we need to be mindful. Oftentimes, the yellow harnesses also will denote airbag circuits. So like if you're inside of a vehicle and you see a yellow wiring harness or connector, that's saying that it's an airbag circuit. So there's a deployable device that is somewhere on that circuit, and they're just trying to highlight that for safety. Here's a look at a fuse panel. This one's calling itself the central junction box. Must be in the center of something, right? We can find where these junction boxes are using programs like AllData and ProDemand and manufacturer websites. Also, the owner's manual may have some good information for us. It's nice to know where the fuses are, like what the designation is, F22, 23, 24, 25, and then we can go and look and see what they actually are there for. So like this F22 should be a 10 amp fuse, and it's there for the audio unit, roof opening panel switch, door lock switch, passenger side, door lock switch, driver side. So that one fuse is actually is acting as the circuit protection for multiple different circuits. Here we have a technician testing fuses to see if they're any good. On these blade style fuses, there are usually little test spots right on top where you can touch on each side and see if there's power on both sides. If my fuse were to break and become open because of an over temperature condition, then I would have power on one side but not on the other, because here's power coming in from the battery. There's an open, so I don't have connection to that same voltage on the other side. So we would just see the test light up on one side and not light up on the other. So these maxi fuses aren't seen that often anymore. We tend to be between these two. These are the minis, and these are just like the regular blade style fuses. And these specific fuses have become more and more popular as well. You can't test these with a test light, but there's a window on the top, and you can actually look down and see, without having to remove the fuse from the panel, that the fuse has been melted and is open. Sometimes a flashlight comes in handy when we come to that, or your cell phone light, I guess, because that seems to be what everybody likes to use. A few different types of fuses as well. Here's a low profile mini fuse, and this is just to make it so that a fuse panel can be a little bit more compact, saving space for maybe some other component, or maybe just the fact that there are so many electrical circuits in vehicles now that they just needed to make more room to put more fuses in. In a pinch, one of these mini fuses will plug in and work, but usually the cover for the fuse panel won't close anymore, so you can use it for testing. And if, like, let's say something comes in with a popped fuse because the switch shorted to ground, if we were trying to diagnose that, it might be nice to be able to pop a fuse in that we are likely to have handy, and if we need to order some fuses from Napa, or if the parts department's all out and they have to order it from like a warehouse or a distribution center, at least that way we can keep on trucking with our diag and keep getting some stuff done. There are also these fuses where it's two fuses, but there's only three blades instead of, if we had two fuses, we'd have to have four blades. Um, these are a space saving item. They're trying to fit more stuff into the same size fuse panel. The problem with these is if one of the circuits pops, well, then you have to replace this whole fuse, and it costs more than just a regular fuse. So, I understand what they're trying to do, but it's kind of a pain in the butt, to be honest with you. Usually on these, power will come in the center, and then you'll go out to each individual circuit from there. The reason they do that is because if power came in here and then went to there and to there, well, if this popped, it would kill both circuits, or maybe even multiple circuits, because usually fuses power up a couple different things, not just one circuit. A resettable fuse is a circuit breaker. This circuit breaker is built with two different types of metal, and as the metal heats up, let's say that we have a short, and these are all called thermal protection devices, fuses, circuit breakers, fusible links, all kinds of stuff like that. And the reason is we're trying to keep stuff from melting and letting the magic smoke out, or lighting on fire, whatever you want to think of it as. So if we have a short and we have an overamp condition, and so this thing starts to get hot, these two different types of metal expand at different rates, and it will pull the contacts away from each other. And usually you hear a little click that happens when the circuit breaker resets itself as these contacts come back down, because there's a fair amount of like a metal spring tension that holds that down onto its contact. The only way that some of these are resettable by pushing on them, and you can actually go in and reset it that way. But a lot of these just cool down and reset themselves. Early blinkers were they were built to overamp a circuit breaker like this. And so the noise that you associate with a blinker, like click, click, tick, tock, whatever you want to consider it as, that device, or the circuit breaker was under the dashboard actually physically making that noise. Now everything's gone electronic, and so people were so used to hearing that noise that now they have programmed it into instrument clusters to mimic that circuit breaker opening and closing and opening and closing, tick tock, tick tock. On a lot of circuits now, because so many things are computer controlled, and this whole write-up down underneath is talking about power windows, which is a good point. Some of these circuits can overamp just because that's the way that they're built. A spinning motor is going to have less resistance. No, sorry, excuse me. A spinning motor is going to have more resistance than a motor that is stationary but still being supplied current. And let's think about a power window. What do we all do? You roll up the power window, and then you want to make sure it's really rolled up, so you like pull up on the switch a few more times, or maybe you're like, I'm going to have a power window race, and you try to roll them all up at the same time and see which one gets to the top first. But when one gets to the top, you don't let go of the switch. And so that circuit basically becomes a short at that point. And on a lot of vehicles, and you can try this on your own, when you roll a window all the way up to the top, oftentimes you'll hear a click. That's a circuit breaker built into the motor opening up, making it so that you can't overamp the circuit anymore. On some vehicles, though, especially ones where maybe a computer is what's actually rolling the window up, sometimes that switch is just sending a voltage signal to a computer in like the door or under the dashboard, showing a request, and then the computer rolls the windows up. Think about one touch up or one touch down, right? You pull all the way up on the switch and the window magically rolls all the way to the top. When it gets to the top, the computer's usually pretty good about stopping or cutting off the current flow right off the bat. But say something goes wrong with the circuit, they add this PTC protection, so it stands for positive temperature control, or coefficient rather, positive temperature coefficient. And what that means is as the temperature of this device, and this is a semiconductor, as the temperature of this device goes up, so does the resistance, which then limits how much current can flow through the circuit. You've dealt definitely with Carl in the engine performance class with things called NTCs, negative temperature coefficient, and that would be something like a coolant temp sensor or cylinder head temp sensor. Those sensors, semiconductors, change their resistance based off of the temperature of the coolant or the cylinder head that they are mounted on. And as the temperature of the coolant goes up, the resistance of the temperature sensor actually goes down, and the computer sees this voltage drop change that happens across that sensor, and then looks into its little programming library to figure out what does 4.3 volts mean versus 6 volts. Alright, so this PTC protection is very similar to a circuit breaker in the fact that we just have to wait for it to cool back off and the resistance will come back down for us. And it's built into some computer circuits, definitely not all, but some computer circuits, and is there to protect things. You'll see it on lighting circuits as well, because sometimes when a light bulb burns out, the filament will drop down into the bulb and can sometimes create a short circuit that way as well, or because it fails by melting, so when it melts it could just create a short circuit. Fusible links. So here at the top is a true fusible link, and all this is a weak part of the wire. So if we have an overamp condition, too much heat, this is the part of the wire that's going to melt first, and they denote that in wiring diagrams so you know where to look for that weak link of the wire. And then here's a mega fuse. You'd see this on the side of a battery or maybe a fuse panel, and this is going to be a fuse that would cut the battery off from maybe even powering up an entire fuse panel. 125 mega, that means it's going to blow at 125 amps. You can see that stamped on the mounting ear right there. Some electrical symbols and wiring diagrams. Every manufacturer seems to have their own take on what these symbols needs to look like. They tend to be pretty dang similar, just slightly different depending on what era of wiring diagram you're looking at or who made the wiring diagram. Your book has a section that has a fair number of these symbols in it as well, and so I recommend that you use that to refer back to. When we're working on stuff in the class, I'm going to try to make it clear as we go along about the schematic and the symbols that we're dealing with really are and what they mean. And as you get some more experience looking at diagrams, you start to be able to kind of figure out what it is that they're trying to illustrate with these different symbols. But knowing what they mean is definitely important so that we can address the circuit in the proper way. Some more. Not standardized, right? Yeah. Everything in the automotive industry seems that way. There's 5 different names for the same thing no matter what you're working with. Our wires themselves are going to have color codes, also not standardized. You can see just some examples here. Black, BLK, BK, B. Sometimes it's a bummer when you're looking at a wiring diagram and you see a B for one of the wires and you're like, is that blue? Is it black? Is it brown? Is it purple? Oh wait, no, purple's not a color, is it? But you see what I'm saying. It can be a little bit complicated. If you're working on the same manufacturer's stuff all the time, then they tend to keep it standardized within their own little world. But it wasn't up until recently that when you looked at a Volkswagen wiring diagram, everything, I don't know, up until like the last 5 years, I think is my experience, they used German colors. And so the first shop I worked at, we actually had a German to English dictionary because some of the words on Volkswagen, some of the wiring colors didn't really make sense in English because they weren't in English, they were in German. And so we would use that to cross-reference. And I'm dating myself a little bit, but that was before everybody just whipped out their smartphone and Googled it. That wasn't really a thing back then. So, books. Four methods of color code. So you could have a solid wire, and what we often see will be either solid wires or a wire with a stripe. So that'd be like a blue wire with a white stripe, or a white wire with a red stripe. On some manufacturers, they might use hash marks or dotted. My father-in-law works for Milton Caterpillar, and every one of the factory wiring harnesses, all the wires are pretty much the same color, but on the wires they have written what the circuit number is. So if you look at a diagram and it says this is circuit C25, and you find that wire, every few inches or so would be C25, C25, C25. I like the colors, but I'm not gonna lie to you, I'm a little bit colorblind, so sometimes that blue and purple wire or the brown and the green wire, hard to tell the difference between the two, and there are tricks to figuring that kind of stuff out too. This is Circa Carl. This has been in here ever since I was a student. So when you see a wiring diagram, don't run away. Pew, little laser sound. I left that in there just because it makes me happy. So wiring diagrams are the best thing ever, honestly, when you're trying to deal with an electrical circuit. Some people roll their eyes about electricity. Oh, I hate electricity. I never want to deal with it. And I get where the struggles can be with some of these circuits. But we're really, really lucky about how much access to wiring diagrams we do have. The information is good. It helps us find where connectors are. It lets us see what the connector looks like. It's a really, really, really useful item and resource. I consider a wiring diagram one of the best tools that's anywhere near my toolbox. But when we look at the wiring diagrams, there are different takes on how things happen. So this wiring diagram next to our little run-in tech is what's called a map diagram. And it's a map diagram because it's showing all kinds of different stuff. It's not just one circuit, it's multiple different circuits. The nice thing about these map diagrams is oftentimes they'll show, these are just images of the connectors. So they'll show the connectors right there on the diagram, so you don't have to go look up the connector view to figure out which one of the terminals in that connector is the one that I want. The troubling thing about these is you're kind of overwhelmed with all the information. There's like a little bit more shown to you than what you really want to see, at least for me. And so this Valley Forge wiring diagram has has been pretty popular for a fairly long time. They call it Valley Forge because we're just going right through forging along this wiring diagram. We've got power at the top, and ground will be at the bottom, so you have a pretty good idea of the direction that current's flowing. Versus this, it's like, well, it could be noodling all over the place. It looks like someone spilled their spaghetti on my computer screen right now. So Valley Forge diagram, and this brings up a few nice topics that I think we should take a little second to address. So hot at all times, this is telling me that this fuse is connected, or this circuit and fuse is connected to the battery always. You don't have to turn the key on, you don't have to flip a switch to get this one to power up so that you can then use it. And it would make sense, it's a horn circuit. You can see our horns down here. We would want the horns to work all the time. Let's say the engine dies or something like that, and we need to hit the horn because we lost our power steering and we're afraid we're about to run into something, or if we're stranded on the side of the road and someone drives by and we want to flag them down real quick. We don't want to have to like fumble with the key, get it back in the ignition, hit the horn. So it's there for safety reasons. On this, you see how around the fuse this fuse panel is all dashed. So that means that we're only seeing one piece of this fuse box. There's much more going on, so they make this dashed line around it so that we understand it. The same thing is happening down here in this convenience center where the relay is located. Here's a splice. And then you see these dashed lines here. That means that there are multiple wires that come out of that splice. And with this Valley Forge diagram, they're only showing us what we want to see. Right? We looked up this horn circuit, but they are letting us know that, if this fuse were to blow, then other circuits would probably not work as well. Or let's say we had a failure with one of those circuits that could cause this fuse to blow, and it doesn't necessarily mean it has to be the horn or the capacitor or the switch down here causing an issue. We also can see, I'm going to zoom in a little bit, so we can see my splice number. It's number 212, and I could actually look up that location online. I also am being shown the gauge of, or the color of my wire, orange, I would imagine, and the circuit number. This is circuit 40. Circuit 40. We come out of the relay, now we're circuit 28. 29 over here. All right, so if we were writing up like a warranty story or something of that nature, we would want to reference what circuit we found an open or a short or corrosion or what have you. Then when we come down here, you can see a connector and a connector number, C for connector 100, just like S for splice 212. So then we know that this is connector 100, that's connector 201. So if I disconnect this one, it's not going to do anything over here. It looks like they must be using the metric system for my wire size or my gauge. And also, I guess with this connector, the other thing I want to say is it kind of looks a little bit bad in this diagram, and we'll be looking at many in the future. But this also shows you which side of the connector is male and which side is female. So the way that this is looking is it's two like chevron looking things. And so what we got on here is the male side of the circuit's on the bottom here. So that's the male pin that would slide into the female pin. So that's really convenient, because if I'm looking to see if I have power here, it's nice to know what side of the connector I would expect to see it on. So I'm not like, well, test here. Nope, I test here. Nope. Okay, well, I don't have it, but I don't really know which way on this harness I need to travel, right? So they're trying to give us as much information as possible. Here, we have some grounds. We also have a ground here, and that's just meaning that the component is grounded by the way it's mounted. Whatever it's bolted to must be a piece of metal, and so that is our ground pathway. There's not an extra wire coming off of this or anything like that. Okay. And then I think that's as much as I really want to deal with for this moment on this diagram. Let's see if I can get on to the next one. Connectors and grounds, splices, sometimes even circuit numbers tend to have some sort of rhyme or reason behind them. So this one here, there we are. So this one here, they're saying for this manufacturer, under the hood would be my 100 series circuits or connectors, 200, 300, 400, so you have an idea of what part of the vehicle that connector or ground would be in, just based off of the number in the wiring diagram, which is pretty convenient. I mean, like, I'm not going to go rooting around forever, but at least I know, like, okay, I got to go under the hood, or if I see one that's like, oh, it's under the dashboard, I don't know, that seems like maybe not the easiest place to get to, so maybe I'd want to be looking for a connector, another connector in that diagram somewhere that would maybe make it easier for me to get to and actually test for voltage or resistance or what have you. When we do these diagnostics and repairs, often what we're trying to do is find a spot in the circuit that I can get to easily and see if I can get as much information as possible out of that one spot before I have to pull a door panel off or start pulling a dash apart or anything crazy like that. Here is a relay, and we dealt with relays in the 150 class, and so I'm sure that you're all experts. We'll deal with relays on our breadboards as well. They're not the automotive style ISO relays, but still a relay is a relay. On the the nice thing about the automotive ones is they always put a little diagram on the side of them so we know how they work. And here's my coil of wire. I send current through, and this is, like I said, going to be between like 50 and 150. Oh, there it is right there, 50 and 150 ohms. And so we're not going to have very much current flowing through here. So like a little computer could handle the amount of current that goes through that. Creates an electromagnetic force that then pulls the switch over and moves it. So this is an electromechanical device. Low current controlling high current. And here's another image of that. Here's my coil, and it just pulls the switch down towards it. You can see the contact points there. There's a little diagram on the side, and that's where its home is. There's a relay working on a horn circuit. So, and that's where they're saying low current controls higher current. Oftentimes on these, and let's see if it shows it on that one. Not so much. Not that one either. But almost all relays are going to have either a diode, which only allows current to go one way, or a resistor. And the reason for that is we've created an electromagnetic field. And just like an ignition coil, when we turn off the circuit, open up the switch, all that magnetism collapses across the coil. And that causes a very, very high voltage to be created, which, in an ignition coil is useful because it makes the spark jump across the air gap of our spark plug. But in the rest of our circuits, it's not so ideal. That high voltage can burn up switches. It could hurt parts of the computer. So if it's a diode that's there, the switch opens, the voltage or the magnetic field collapses, voltage is created. The diode just allows that current that's created to flow through the coil a couple of times, and the coil has resistance, so it drops the voltage that way. Or if we have a resistor, this resistor is there to eat up that voltage before it can go and burn up some component that we don't really want burned up. Typical wiring diagram. I just think this is nice because it illustrates how one fuse can be the circuit protection for many, many different circuits. And because all these circuits are in parallel, that means this fuse needs to be amperage rated high enough so that if all these circuits were working at the same time, it could handle the amount of current that's flowing through it, because it would be this current plus this current plus this current plus. Get the idea? That can be problematic when just one circuit has an issue. Like, say I have a short here to ground before this bulb. It would take a little bit longer for this fuse to pop than if the fuse was just dedicated for this one circuit. Instead of being a 15 amp fuse, it might be a 5 amp fuse, or maybe even less. So sometimes the fuse might be a little bit more robust than what we would expect, but 15 amps is a lot less than infinity, so it's still definitely going to pop when we have a short. And this is very common in automotive wiring, to have one fuse be a circuit protection for many, many different things. Here's our little fuse panel. Now, we've talked a lot about fuses and a lot about fuses popping, and you have an issue, you go, and the first thing a lot of people will check is the fuse, because it's pretty easy to get to, and there's lots of good information usually to help you figure out what fuse it is that you need to look at. But if we have a popped fuse, that is not an opportunity to be like, oh good, I can just put a fuse in this and it'll be fixed and everything's good and hooray. Something has gone wrong to cause that fuse to pop. Someone could have tried to jump start a vehicle backwards. That can often pop mini fuses and maybe some computers. Maybe a component is intermittently shorting itself out. Maybe a wiring harness has to be moved or vibrated just the right way to make contact to ground. But when we have a fuse pop, it's usually going to entail like a fairly lengthy diag, because we're trying to figure out where our short is. Alright, so not a great thing usually. There's talking about using a test light, like we talked about before, to test both sides of the circuits. And then these next couple of slides deal with a short circuit tester. What they do is they call it a tone generator, but you hook up this box into the terminal where the fuse used to be, and that box will just pulse a voltage every so many seconds, or once a second maybe. And what you do is you go along with either these ears or old school. I had a tech that had one of these and it seemed like magic, but when current flows through a circuit, it creates a magnetic field. So you can follow the magnetic field along the circuit. So when it pulses, you should see the needle move, needle move, needle move. And when you get to the point of the short, once you move past it, now there's no more current flowing, because the current, as we move, right, the needle is moving every time it pulses. Oh yeah, magnetism, magnetism. We get here, and the voltage or the current flows to the short because that's low resistance and easy, and anything past that won't have any current flowing through it, or not much to speak of. And so then all of a sudden the little needle would stop working. Or if we're using our high-speed headphones that can pick up noise from the tone generator, then we would stop hearing noise as we went along as well. Now these things are nice and they actually do work pretty well, but it's not something that's common for every tech's toolbox. Something that is common for every tech's toolbox is a test light. And what I often recommend doing is just instead of using this whole thing, take a test light and put one end of the test light on the power side of that socket where the fuse goes, and then put the alligator clip with like a paper clip or something like that on the circuit side of the fuse. And then that test light has resistance, so it will drop voltage across it, and as long as the short circuit is present, the test light should be lit up because we have a place for current to flow. Then as you go along, you can just start disconnecting connectors or pulling bulbs out until all of a sudden the test light goes out, and now you have found the source of your short circuit. Sometimes even going along and like flexing or wiggling a wiring harness will do some good for you there as well. So that's my preferred method because I definitely have a test light, and so do most other people. All right. Now we're going to start getting into some of our electronic components. So in your test kits, your electronics kits that we're using for lab, you got a bunch of resistors. And this is a 4-band resistor. The ones that we have are 5-band resistors, and I talk about that briefly when you look at the unpacking video of me going through and kind of talking about what all the bits and pieces are inside that electronics kit. The banding of the resistor is there to denote what the resistance value is. All right, and I have a link to a website that you can just like choose the colors of the bands, and it'll tell you. The kits come with a card that explains the way that the banding works as well. And the easy way, honestly, because, like, is that red or is it orange, right? The easy way is just hook your meter up and test the resistance value, and we'll be doing that in this first week's lecture. So you'll have the opportunity to play around with all of those things. A capacitor. If anyone's ever wired up a radio before, they've played with capacitors, but a capacitor is like a static electricity battery. So when a capacitor is hooked up to a circuit, there's like an air gap. Usually there's like some paper or some sort of dielectric compound that is creating a buffer between my negative plate and my positive plate. And what happens is that air gap is really, really, really small. And so it still makes the positive and negative charges, it brings them close enough together that they are actually attracted and some current will flow. And then when we disconnect the battery, the current all tries to go back in to the battery again or through a load. And I've got a couple of, there's the slide there. So we'd charge up the capacitor this way. Usually you want some sort of a resistor there because the capacitor can really soak up a lot of current really quickly and let it out really quickly as well. And then we cut off the connection to my battery, close the switch to create this loop, and the current will still flow through the resistor, right? It charges up, and then it would flow in the opposite direction, which can make some really interesting things happen. Capacitors are inside of computers and do all kinds of really great stuff for electronic circuits. The way that we often will see a capacitor is in some sort of a protective capacity. Capacity. Kind of interesting how those two words kind of work together, right? How much capacity does your capacitor have? They're really good at dropping interference. So any AC current is just going to go right through a capacitor. Capacitors are really only useful to store direct current, but it makes it nice because they're used as noise suppressors. Oftentimes you'll see them near ignition coils. They're trying to suppress noise there. They'll often be attached or very nearby to like our antennas or built into our radios, and it's all there to try to knock down any kind of radio frequency interference or electrical interference so that we get nice clean broadcasts. Also, sometimes these capacitors are used because the amount of current that's caused by like a ignition coil firing could interfere with some of our sensors since there's not that much current flowing through those wires. So they're oftentimes just there to try to keep everything as clean as possible so we don't get any weird interference causing issues with radios or with sensing circuits. There's a big old capacitor that would be used for like a subwoofer. When a sub hits, it often will try to pull more current than the battery can supply. And think about noise and songs and stuff like that. It hits and it happens very, very quickly. And so often with bigger subwoofers, you have to add a capacitor because the battery just can't keep up. The chemical reaction in the battery is not fast enough. So there's a capacitor that's built into the circuit to kind of act as a second battery and a battery that can charge and discharge very, very quickly. When you install one of these in a vehicle, they often will send a resistor or a light or something like that, because if you hook the capacitor up without any kind of resistance in the circuit, it'll often spark a whole bunch. Sometimes it can even like really hurt a battery. I've heard of batteries blowing up when someone has tried to install really big capacitors. And it's just because the capacitor is like a black hole until it's charged, and it just sucks up so much current that it creates over temperature conditions. You might hear people talk about, like you got the big glass fuse that comes with these cables, and they'll pop the glass fuse when they're trying to hook the capacitor up, and then they got to go find another one, and they're not that cheap, and they're all angry about it. They wanted to listen to their cool subs and, complaining. That's how that kind of stuff tends to go. We've got this often or these next slides are pretty much going to deal with like sensing type circuits and some semiconductors that we'll start to see in wiring diagrams and start to use some of when we go and start working with our future labs. This is a thermocouple, and the thermocouple is, you can buy them for your meter, and you can measure temperature with your meter. Most meters have a temperature setting, and it's just two different types of metal, and if you heat them up, then they're right next to touching each other, and with heat they allow or actually create current flow. So this is basically like an electrolysis type thing, and heat is just speeding the chemical reaction up. And a galvanometer is just a meter that can pick up very, very low voltages. Okay, so thermocouple. This is not the same thing as like what our temperature sensors in the cars are. Those are thermistors. So it's a resistance thing versus a voltage creation thing. Here's a photovoltaic device. So when light is supplied to this device, it actually creates a voltage of its own. Um, so it's pretty interesting. Piezoelectric device, so you could think of like a knock sensor would be just about the only thing on a car that is this style. But the pressures of detonation or pre-ignition will cause that sensor, they're tuned to a certain frequency for whatever detonation and pre-ignition, the frequency that will happen at a specific motor and through the metal, whether it's aluminum or cast steel. And so you hit the right frequency from one of those events happening, and voltage is created. That voltage shows up in a meter or shows up in a computer, and the computer goes, "Oh, that's not good," and it retards ignition timing. It might mess with the fuel control a little bit, but it's trying to save the engine from cracked pistons, holes, and stuff, cracked heads. Here is a potentiometer, 3 wires, and we'll look at this stuff again, I promise you that. But this potentiometer has power and ground supplied to it. And what's happening across this resistor here is I'm just dropping voltage. These are most commonly connected to things like throttle position sensors, but really almost every position sensor, aside from like wheel speed and crankshaft and stuff like that, are a potentiometer. So as the wiper moves across this, it picks up battery voltage, less than battery voltage, half of battery voltage, less than half of battery voltage, no more voltage. All right, so 12, 10, 8, 6, 4, 2, nada. Very, very useful, and this wiper would move when the throttle opens or closes, or when the seat moves forward or back, right? We need position sensors if we have memory seats. The little mode door actuators for our doors inside of our dashboard have these attached to them so that the computer can see like, oh yeah, the thing actually moved and it's in the right position. So this stuff shows up a lot of times. This is just power, this is just ground, and this signal wire in the middle, this is the one that's going back to the control module and is the sensor input wire. So that's the only one that the computer actually even cares about. Sometimes a computer will supply the power and the ground to these sensors, and that's just so that it can send out what's called a reference voltage. Reference voltage could be 12 volts, or it could be 5 volts, and what they're talking about with this whole reference voltage is it's a clean 12, it's always 12, or it's a clean 5, it's always 5. I sent in your kits a voltage regulator, 5 that would regulate down to 5 volts, and we'll play around with that and use some sensors and stuff to see how that kind of thing works. I sent you those so you can see that clean voltage and see how it works. On our car, if I just turn the key on, then I got 12.6 from the battery. When I start the vehicle up, the charging system comes on, and all of a sudden I'm up around 14 volts. Well, if I want to know exactly what the position on my throttle is, but I just added 2 volts to the scale when I started the engine up, that makes the calculation tough. And we know the charging system's not always charging it at the exact same voltage. Sometimes it's charging more, sometimes it's charging less. So it's pretty important that we have that clean voltage so that we actually know that the information or the voltage that's coming through this wire means exactly this. It's exactly at 33% throttle angle, right? I don't want it to be like somewhere between 20% and 45%, or somewhere in that range. The vehicle's not going to run very well if we don't have these exact values. This looks very similar to a potentiometer, but this is a rheostat. So this would be more often used as like a dimmer switch. So if you can like make your instrument cluster backlighting brighter or dimmer, it's probably going through something like this, where there's no ground pathway coming off of this resistor. It's just we're adding or subtracting resistance from the circuit, which means that we're going to have a little bit less current flowing, and there will be less voltage for our light bulbs or whatever component it is to use. And so if you think back to watts, you figure out watts with voltage and current. And if I've got less voltage and less current, then I'm going to have less work. So whatever my load is on this circuit is going to do less of what it's supposed to do. And that's the end. We've done it. You've listened to me talk for such a long time, but I'm still pretty positive it's shorter than it would have been if we were sitting in the class on a Tuesday morning. Hope you're doing well, and I will see you next time.